Hi, my name is Emma Lotus, and I'm a PhD student at the GFC Potsdam doing a project on geomorphology. I'm working with Dirk Scherler, and I'm in the second year of my PhD. And I'm going to tell you a little bit about the motivation of my project and some very preliminary results. So my project is part of a larger project called Earthshaped by Biota, and the goal of that project is to understand how biota, so plants and animals, influence landscape evolution on a climate vegetation gradient in Chile in the coastal Cordillera, which is a granite batholith. It's a mountain range on the coast in Chile. And specifically, my PhD, I'm looking at and investigating the ways that erosion and weathering affect landscape evolution along this mountain range. And specifically, what are the processes of erosion and what are the controls on erosion and landscape evolution? So these controls include biota, climate, fracturing of the bedrock, and lithology. So erosion by rivers is one of the primary controls on the morphology of landscapes. And rivers, they record the balance between constructive forces like tectonics and destructive forces like climate. The incision or the erosion by rivers is specifically controlled by the upstream area, the slope, and then this parameter that includes climate and lithology called K, and other factors. And this parameter is not well constrained. So part of my PhD is to further understand this. How much does climate affect erosion and river incision? How much does lithology affect this, and etc. So in the Earthshape project, field sites are along this climate gradient I mentioned. And we already understand that more rain generally leads to higher erosion rates most of the time. But how strong is that influence, and how much of the differences in erosion rates that we're seeing are influenced by other things like tectonics and bedrock erodibility? So one of the ways that bedrock can be more or less erodible is if it's fractured. If it's highly fractured, it's more erodible. So that's one thing that I'm looking into in my PhD. So we do know that fracture spacing, fracture density affects weathering and erosion. And that's because when bedrock is highly fractured, the water from precipitation, for example, can enter into those fractures and lead to higher rates of chemical weathering. And that chemical weathering reduces the block size. So tighter fracturing, more dense fracturing, and also more chemical weathering leads to smaller blocks, smaller grain sizes. And those grains are, when they're smaller, are easier to transport down the hill slope and are also easier to transport down a stream channel. And they can also act as tools to erode the stream channel itself. So a wider fracture spacing will lead to larger blocks. Those are harder to transport, and they can actually block the hill slope or block the stream channel from further erosion. So these fractures themselves, they come from depth, and they're exhumed as the bedrock is uplifted by tectonic forces mostly. And the fractures themselves also come from tectonics, usually, from the tectonic stress field, from larger scale tectonic plate movements. But they can also come from topographic stresses as the bedrock is exhumed. So in one of my field areas in Chile, in the farthest south one, we tried to find out how much, whether these fractures that we're seeing in the bedrock are influenced by the tectonic regime. So what we did is we measured fractures in the bedrock, and we also got the orientations of major regional faults and also of the streams in that landscape. And we found that the orientation of the faults, the fractures, and streams all were relatively similar. And that tells us that the fractures are tectonically induced, most likely, and also that streams orient themselves along these weaknesses that are controlled by fractures, which are controlled by the tectonic regime. But then the next step is to actually quantify the erosion rates in more highly fractured areas versus less fractured areas to see how much of a real effect that has. So how we quantified it is by using cosmogenic radionuclide dating. And the way that works is cosmogenic radionuclides, such as beryllium-10, which is what we used, come from the atmosphere, come from cosmic rays, and they accumulate on the Earth's surface. So the longer material is exposed to the atmosphere, the more cosmogenic nuclides it accumulates. And then by measuring the concentration of that nuclide, we can find out how long the material has been exposed to the atmosphere. And in material that's actively eroding, such as in an uplifting mountain range, you can also get the erosion rate based on those measurements. So we collected samples from areas with more and less fractures, and also measured the fracture spacing in those areas. And also, in some cases, we measured the width of core stones as a proxy for fracture spacing, which is something that's illustrated in this cartoon you see on the slide. So for each sample, we took an amalgamation of over 10 chips, and we put those together and got an average erosion rate that's representative of a certain fracture spacing or a certain core stone width in some cases. We also took samples from soil, which we amalgamated in a similar way over an area of roughly 10 by 10 meters. So we measured these erosion rates, and in the end, we found that bedrock that had higher fracture densities tended to have higher erosion rates as well, and soil was eroding much faster than the bedrock. So that leads us to conclude that areas with lower fracture density are either already are or most likely will become areas of topographic highs. So hilltops or ridge lines that are eroding slower than the rest of the landscape because they have a lower fracture density. And we also found that the variation in erosion rates between soils and bedrock of different fracture densities was larger than the variation of erosion rates between the climate zones from which we sampled. And that's something that we are going to be looking into more as the PhD goes on, and something that can be really interesting in constraining how landscapes respond to differences in climate and differences in bedrock strength. And stay tuned for more to come down the road. Thanks.